Okay, so welcome to February the 8th, 2021, today's lecture in Emergent States of Matter. So last time we talked about the idea of different microscopic spin configurations, as shown here on the left board. If I coarse-grained those by making a sliding variable, a sliding coarse graining, a sliding average of the local spin directions, I would then get some smoothly varying variable that describes the order in the system, and that's plotted down here as the coarse-grained magnetization, where lambda is the size of the window over which I'm averaging, and that's reflected in this subscript over here, and the precise definition is given by this equation here. So the idea was that both snapshots of the system, both microscopic system number 1 and microscopic number 2, both had the same coarse-grained picture of the system. And so we have the idea then that different microscopic states, if I coarse-grain them, will flow to the same large-scale state. And we introduce this idea, this term, coarse graining to describe them. So what I want to do today is I want to ask the following question: what is the free energy that describes the probability distribution for the configurations m lambda of x? In other words, if you tell me a spin configuration, I can tell you what is the Hamiltonian of the system, and I can tell you what is the probability of observing that microscopic state just based on the Boltzmann distribution. But now if I've got a coarse-grained state, m lambda, what is the probability distribution that describes that? And that's what we're going to calculate next. And that's going to lead us to the idea of a mathematical quantity called a functional, which is the way that we're going to be describing the system. And so I want to lead you to some very simple manipulations on functionals, functional differentiation and functional integration that we'll be using throughout this course. And then I want to talk at the end about systems with continuous symmetries. So for now, we're just going to be still talking about spins that point either up or down. So these are Ising model type symmetries, discrete symmetries. But at the end of the lecture, we will talk about systems with continuous symmetries. So the question that we want to discuss then is if we work at the level of description of m lambda of x, what governs its statistical mechanics? And in other words, the analogy is this: if we work at the microscopic level, so the state of the system is described by the variables SI, then we know that the probability of observing the system in some particular state SI is proportional to e to the minus beta times the Hamiltonian of SI. So we know that that's true. So our question then is, if I now say a configuration is now described by this continuous function m lambda of x, something that looks like this over here, what is the probability distribution for that? And we're going to see that this is proportional to something called the Landau free energy. And we're going to construct that and understand what it actually means. So this is going to be our answer, and so our goal then is how to construct this object. So the way that we're going to approach that is we're going to approach it by looking at the symmetries of the system. and we're going to look at the symmetries. We're also going to worry about analyticity. I'm going to explain why we do that. And then the other thing that I want to point out is that we know that the equilibrium state of the system is spatially uniform. And so then we have to ask then, if we have an m lambda of x, which is not spatially uniform, then that means that spatial variations must cost energy. And so then the question is, how much? And how do we quantify that? So those are the ways that we're going to construct the free energy of the system, or at least the lambda, this quantity L. So let me just write down here that this quantity has a name. So this is going to be called the Landau free energy density, or the Landau free energy in this particular case, because Landau was the person who first developed this line of reasoning that I'm now going to show you. So the basic idea is that to construct L, it should have the following terms. So the first thing is it should be, actually let me call it A. So the first thing is that we expect our system to be rotationally symmetric. So therefore the terms that we write down should be rotationally isotropic, or rotationally covariant, I suppose would be the more precise way to say it. We also expect our system to be translationally invariant. Then the other thing we want to understand is that when there are spatial variations, those spatial variations, it's the gradient of those things that matter rather than the absolute magnitude. So the Landau free energy, or this free energy, should depend. Or let me put it this way. Let me write it as this. It should penalize deviations from spatial uniformity. It should also be local in space. And then if we're near the transition, we expect m to be small. And so that means that it should be an expansion in powers of m, and we keep the lowest order terms. And then the last consideration is that it should be analytic. And the reason it should be analytic is because when we constructed the coarse-grained order parameter, so here is the formula for that over here. Where is it? Yeah. So here's the formula for that over here. So you can see that what we're doing is we're summing over the spins that are within this sliding window. And so what that means is that what we have over here is a finite number of degrees of freedom. Okay, we're summing over a finite number of degrees of freedom in making these windows. And so what that means is that we expect that because we're summing over a finite number of degrees of freedom, when we work out the probability distribution for those sort of little blocks of degrees of freedom, since you're adding up e to the, Boltzmann factors, e to the minus beta times the energies for a finite number of spins, then that must be the sum, the finite sum of a bunch of analytic functions has to itself be analytic. So the reason that this is analytic is because each m lambda of x is a sum over a finite number of degrees of freedom, in this case number of spins, and so the stat mech of them must be analytic. And specifically, when I say the statistical mechanics, what I mean is that the partition function is only a finite number of terms, and therefore must be analytic. So that's how I must construct this free energy. So let's think about what that means. So the first thing I want to ask about is the
Nigel?
variable is what governs the spatial variations. Yes, question?
Yeah, no, just really quick. It's like super hard to see the color that you wrote the partition function text in, at least.
Yeah, I agree with you. It is.
Okay.
So let's see. Can I make it better if I highlight it? Nope, that just totally made it worse. That was a really bad idea, right? Okay, is there a way for me to change the color? I don't know. Okay, can I change the color? Nope, I don't know. Can I change? Oh yeah, color. Okay, let's make it green. There, problem solved.
Perfect. Thank you.
Okay, thanks for the point. Okay, so let's first of all talk about spatial variations. So if I'm going to write down something that penalizes spatial variations, that means it's going to have to be gradients of m. Okay, so that means things like grad m lambda of x. It's got to involve that. And if it's going to involve that, it's got to be analytic. So it's got to be rotationally covariant. It's already translationally invariant. This term already satisfies point C, point B, point D, point F, and if I can make it rotationally covariant by just squaring it. So if I make this squared like so, and then integrate over all of space, then I've accomplished my representation of the energy cost or the penalty for having spatial gradients. So this gives me a penalization of departures from spatial uniformity. So if m is a constant, this term will be 0. If m fluctuates, has a positive gradient or a negative gradient, because of the squared term, each deviation from uniformity, regardless of whether it's a positive or negative one, will still give you the same energy cost. And so this thing, we're going to multiply it by some coefficient that will tell us the energy cost of these spatial variations. So that's fine for the spatial variations. Now we already saw what the free energy must look like for the terms that don't depend on space. Okay, and so where did we see that? Well, that was what we did last time. So that is this free energy over here. So this is just writing out what we saw explicitly for the Weiss mean field theory or for Landau free energy, just this particular functional form. But this was here, this eta was the system-wide magnetization. So eta was the total magnetization or something like this. So now we want to make it local. So what we're going to say for now then is that for those terms, we're going to say that L is now the integral over space. And I'm going to write it like this. Then this term that I already wrote down, so 1/2 grad m lambda squared, and we'll put a coefficient in here in just a minute, and then those other terms that we wrote down before, the quadratic and the quartic term, but now we're going to make them functions of space. So there would be eta. Now, sorry, I'm calling it m, so let me write it as m for now, but later I'll call it eta. So then you would have m of lambda of r squared. You'd have a term m lambda of r to the 4th. You'd have a term, an external magnetic field at r times the magnetization at r. And then you would take all of these things and integrate them over space. And then you would put in coefficients in front of all of these terms. And that's the wrong color. So you put in a coefficient over here, a coefficient over here, and a coefficient over here. And so this by symmetry is what we would expect the free energy to look like. So any questions about how I wrote down this particular form for the free energy, its particular functional form?
I have one question.
Mm-hmm.
So are we treating m like a vector now instead of just a binary up versus down?
No. Now
Okay.
This is just a scalar number. It's just a number between 0 and 1 or something like that.
If it's just a scalar number, what is preventing us from having a linear m term without it being coupled to the external field? Normally, I'd say it's the rotationally covariant if it's a vector, but since it's just a number,
it's not that. It's the fact that that when I differentiate the Landau, the free energy, and require that that m being 0 is a solution, that means there cannot be a linear term.
Okay.
So we saw that last time. I didn't really emphasize that. But remember, what we do is we minimize we take this form and minimize it with respect to n in order to find what the state of the systems are. And so in order for that to give you eta equals 0 being a solution, there can't be any linear term because that would give you a constant Peter.
Okay.
Okay.
Thanks.
Thank you. Yeah, thanks for the question. So note that there is no constant term because we want m equals 0 to be a solution. So that's the first note. And the second note is that the coefficient of m squared should be proportional to t minus tc over tc. And then there is no m cubed term. And the reason that there's no m cubed term is that we know that in the case that the external magnetic field is equal to 0, there should be time reversal symmetry. Meaning that if I replace m by minus m, the free energy should be the same. So this is just the same thing as saying that the Hamiltonian, the Ising Hamiltonian, when I flip all the spins in the external magnetic field, gives you no change. So this is the same as H of SI equals H of minus SI when the external magnetic field is equal to 0. And we saw that last time in the way, well, when we wrote down the Ising model Hamiltonian somewhere back here. Yep, we saw that back here. Okay, so this is just the free energy manifestation of the original symmetry of the Hamiltonian. Okay, so everybody happy with that?
I have a question. What about higher derivative terms?
So you could add higher derivative terms. So so if I had higher derivatives, so that would be in K space. We have so grad m squared is going like K squared m squared, and if I had higher derivatives, say this or something like this and so on, then what I would have, I'd have k to the fourth, mk to the fourth, and so on. And so because those are high k, what that means is that those terms don't matter at long wavelengths. So in other words, what I'm saying is we are primarily interested in the long wavelength behavior, so the lowest order deviations from spatial uniformity. And when I say lowest order, in terms of the wave number. So anything that is a higher derivative will give me corrections for smaller and smaller wave numbers, for smaller and smaller wavelengths, but we're interested in the long wavelength description of the system. So did I answer your question?
Yes, thank you.
Can I ask a question?
Yes.
So what do you mean by no constant terms? Could you explain that again?
Could I explain why there is no constant term? Why is there no linear term here other than the coupling to the magnetic field? That's what the question was.
Okay.
So if there was, then if I look for the solution dl by dm is equal to 0, imagine that I put, for example, L was equal to a m plus b m squared plus c m to the fourth. Okay, so now I want dl by dm to be equal to 0. So that means I get a plus 2b m plus 4c m cubed is equal to 0, right? And I want m equals 0 to be a solution. Because I want there to be a solution where there is no net magnetization. And so that means that I need to have A is equal to 0.
I see. Okay. Thank you.
Sure. Okay, so let's keep that in here. And let's go on to the next thing. So the next question that we should ask ourselves then is, well, this is great. So how do I get thermodynamics from this? So the answer is, it goes like this. So what we know is that if we want to know what the free energy of the system is, of a system described by statistical mechanics, that is equal to the partition function. And the partition function is just the trace over the microscopic degrees of freedom of e to the minus beta times the Hamiltonian, like so. So that's how that defines for us the Helmholtz free energy. And so what this means here is, as we said before, sum over all the degrees of freedom. And so in this particular case, the degrees of freedom are the spins. And we're going to sum over their values, which are plus or minus 1. So that's what that thing means. So this is what happens at the level of description of the microscopic degrees of freedom. Okay, so now let's ask, well, what would change if we were to do this for the non-microscopic degrees of freedom? So let's just write it down, and then we'll ask what it means. Okay, so the formula is e to the minus beta f is the partition function. Let's just write down that this is partition function. And what we do is we take the trace over all degrees of freedom of this thing over here. So now we've said that in going from the description in terms of SI to the description in terms of the, I'm going to call this variable R, in terms of the magnetization, the local magnetization that is coarse-grained. So we've coarse-grained from there. So this thing is governed by the Hamiltonian of the system. And this thing is governed by the Landau free energy of the system. I'm going to write the Landau free energy of the system to be like this, but I'm going to say more about this in a minute. And this L is the same thing that I have over here. So that's what we mean. And so what that says is that if I literally just make this identification, then what I should say is that the partition function is going to be then the trace of e to the minus beta times L of m lambda of R. And so the question is, what does this mean? And so literally what it means is we have to sum over all possible degrees of freedom. But what we have now is a function rather than a possibly huge vector of spins SI. So then what this trace must mean then is that what this trace must mean do some integral over all possible functions m lambda of r. And so we're going to need to know, how do we do this? What does this actually mean? So conceptually, that's what we want to do. So this is the conceptual idea. And then we have to figure out, how do we do this in practice? Okay, so let's talk about that. So I want to now discuss functional integration and functional differentiation.
Hi, Nigel. I have a question.
Yeah.
So I know we had an ensemble problem before, but how do we know we're using the right ensemble here? Wait, the right, sorry, we had the bulls, like, I know previous class you mentioned that we had the ergodicity breaking and there was a...
So we get exactly the same thing here.
Okay, so the distribution which we have used is still incorrect, the e to the power.
Well, so for the moment, I'm doing this in a finite system. So in my finite system, so when we write down this integral here, this is the integral over a finite volume V. And when we take the thermodynamic limit, then we can get the functional equivalent of ergodicity breaking.
Okay.
So everything we said before. So for now, we're just going to be talking about a finite volume.
Okay, thank you.
All right. Good question. Okay, so let's talk about our two levels of description. So we have the variables SI, and then we have the variables m lambda of r, and they have multiple differences. So the first thing is that this variable is discrete, meaning that SI can have values plus or minus 1. On the other hand, this variable is continuous, and and a real function. So that's the first thing. The actual variable itself is discrete and continuous. And then, apart from the variable, we also have the label of the variable, which is I in the discrete case and R in the continuous case. So this thing here is a label. And the label tells you which variable you're talking about. And this label is also, I itself is discrete and on a lattice. And here, R is continuous. And in free space, I suppose. So these things differ in terms of the label and in terms of the variable. So there's two things. So the label, so space is just a label, and the variable is the order parameter. So you'll often hear me say this, whenever we do any manipulations in functional calculus, students will get confused, and I'll say, don't get confused, just remember that space is just a label. So if you're ever in doubt, just think of it as a label, a subscript, and it's just like doing partial differential calculus or vector calculus for a countable set of discrete variables. Okay, so now the question is, so we've talked about coarse graining. Is how we went from the S variable to the M variable, like so. So let's talk about how do you go from I to R. So let's just think about that. So what you might say as well, on the original side, I have some lattice like this. So the spacing here is A, and the volume of the system is the number of lattice points times A to the D, where D is the spatial dimension. And then on the other side over here, what I can have is I have literally the box of the system, like so. So it has some volume that's like this. I don't see any lattice because what I've done is I've taken the limit A is going to 0 and N is going to infinity and V is still finite. So it's the same V as I have over here. So you can imagine, as what I've done is I've taken those things, those lattice spacings, made them go continuously to 0, and so this is the continuum. And versus it's discrete. So you could say, well, all right, I can make an intermediate level of description. And in my intermediate level description, I still have a lattice, but I have a continuous order parameter. And so what I have then is that the I goes from 1 to N is still discrete, but on each lattice site, we have a scalar number, m of I, and this has values from minus infinity to plus infinity. It's just some real valued number. It's not plus or minus 1. So this is some intermediate level. And then if I take the continuum limit of this, then I will have the thing that I want. So if I do that, then I might ask, well, what would the trace variable be? What would the trace function be in this kind of description? So now what I would mean by trace would just be very simple. I would just go through every lattice site in the system. and then I do an integral of the values of the order parameter at those sites. So basically now what I have is a big multiple integral of the m variables at all of the lattice sites. So this is some actually take that away. This is a huge integral of variables of n over n sites like this. So this is just some big multiple integral. But in order to get the continuum limit, I need to take n goes to infinity. And so if I take n goes to infinity, then what I'm doing is now an integral in an infinite dimensional space. So we need to figure out what do we mean by doing an integration in that way. So the basic idea to do this technically is to do it in Fourier space. So let me write down the let me call the variable. For now, I'm going to call the variable eta rather than m. Okay, and so on. I'm just changing its name because this applies in general, not just for magnets. So then what do we expect to happen when we try to represent the Fourier components of this variable or the order parameter? So remember, it still has this label lambda, so it is a coarse-grained order parameter. And so because it's coarse-grained, what that means is that it does not have length scales smaller than the windowing size lambda, because we've averaged over those. And so that means that when we look at the Fourier components are going to be 0 or very small when k is greater than 2 pi over lambda. And so the way that we will write this down is so now we will assume that we've done some windowing. So when we say small, what we mean is basically 0, at least from when k is much larger than this number here, for the small wavelengths. And so now what I want to look at is what happens when I try to Fourier transform this variable. So the Fourier transform is going to be defined like this. So that's how I'm going to define the Fourier transforms. And notice that eta of r is real. And so that means that eta of r is equal to eta of r complex conjugate by n star means complex conjugate. Okay. So what that means then, if I take the knowing that eta is real, so if I from these equations, if I take that and take its complex conjugate, what that tells me, and you can check this, is that the real part of the Fourier transform is equal to the real part of eta for minus k, and the imaginary part of eta of k is equal to minus the imaginary part of eta of minus k. So just check that for yourself, that you understand where that comes from. So just because we have a real variable, it means that the negative k components, Fourier components, are not independent of the positive k ones. So that's a constraint. Okay, so the advantage of going to Fourier space is this. Is that for a fixed v or finite, the k values for say for periodic boundary conditions are quantized. And so because they are quantized, that means I have a countable sum of those, and so so basically what that means is that to integrate over the functions f lambda of r is the same as integrating over all the functions eta of r is the same as integrating over all Fourier components. And we know that we have a discrete set of those. So basically what that says then is that when I write down this trace operation, what I'm going to be doing is I'm going to be integrating over the real parts of eta of k, then the imaginary parts of eta of k, and then I'm going to be doing this for all k values, and those k values have to have a magnitude which is less than 2 pi over lambda. And so I've got a finite discrete set of wave numbers which label these Fourier components, and then this is just a big multiple integral in k space. So again, I want to make this important point that k is a label. And so when I integrate over, when I do this multiplication here, so I'm just this is just the product of integrals labeled by k. Okay, so there's one more thing that I have to do. We're not quite done yet, because the other thing that I haven't implemented is the fact that these variables are not independent. So if I integrate over all of the variables, over all the labels k, we are getting everything twice. And the reason for that is because the k and minus k are not independent. So what we have to do is only integrate over half of k space, and so we can do that, for example, by saying we'll just set the z component to be in the positive half plane and the others to be anything we like. So in the end, what we get is that the trace operation is going to be the integral, the product over k is less than 2 pi over lambda. And we're also going to require that kz, the k component, should be positive. And then the variable that we integrate is the real eta of k, the imaginary eta of k. So the variables of integration are these Fourier components. And how many of them are there? Well, they are just labeled by the k values. So we typically, we will call this, we might sometimes write this as the trace is the integral d eta of k, and this is called a functional integral. And this is in k space, or we might do it in real space. If we did it in real space, we might say that trace is the integral like so, and this is really, when we write it like that, what we are doing is integrating, is doing this one over here, and then taking the limit as n goes to infinity.
Is there any reason that we need to integrate over just a half space instead of just like dividing by 2?
Yes.
Okay.
It is, because when it's not that the result is divided by 2, it's just that the region of this of space that we integrate over is divided by 2. So actually, what will happen?
But isn't there symmetry?
No. So it will end up being that when we write down the free energy, the e to the minus the free energy will end up, the free energy will be an integral over k, and the factor of 2 will come in the exponential, not in front of this whole thing. Okay, so remember this is the label. So we want to keep it like this, because when we actually do the calculation, where we actually do the k integrals is going to be in an exponential, not just out in front. You'll see that in a minute. Okay. Okay. So this is known as functional integration. And now I want to talk about, well, what is a functional? And what else can we do with functionals? So the answer of what is a functional is that it is a map from functions to numbers. Okay, So let's just be clear about what we mean by that. So when we talk about a function, that is a map from a number to another number. So it's basically a machine. And if you put in a number, then out comes another number. So that's what we mean by a function. So what is a functional? So what a functional is another machine where I put in a function and out comes a number. That's all it is. So there's a familiar example that you've known for years, and that's an integration. So if I have an integral like this, the integral from a to b of some function f of x dx, that gives me a number, which we'll call I. And in order to get that number, you tell me what f of x to put in here, and I'll tell you what number comes out. So we can say that I is a functional of f of x. Okay, so that's all that a functional is. All right, so you've seen them before. So now that we've talked about functional, we've talked about what a function is, and we've talked about functional integration, then you might ask, well, can we do differentiation for functions? And the answer is yes. So let's talk about what a functional differentiation is. So the best way perhaps to think about this so as not to get confused is to think a bit like this. We're going to approach this by first discretizing the space label R to a lattice label I. So what that means is that so our function is going from e to r to a set of values defined at points in space I like this. And so that means that our functional of e to r now becomes a function of a set of variables e to I. So this here, on the left here, this is a continuum. And this over here is discrete and enumerable or countable. So let's suppose then that I want to differentiate with respect to one of these variables. So f of eta of I is just a function of many variables. So then, so I can do partial differentiation. So I can just write df by d eta I is the limit as epsilon tends to 0 of f, or I'm going to write down the variables explicitly, eta 2, eta 3, eta I plus epsilon, eta I plus 1, and so on, minus f of eta 1 up to eta n, and then this whole thing divided by epsilon. So that's what I mean by a partial derivative. And what is important is that you tell me which eta variable you want to differentiate with respect to, which label, and then that is the one over here that has the epsilon added to it, and then we subtract just the function without the epsilon and then divide by epsilon. So these i's are the same. And so I can think of this then as saying that df by d eta j, I could write this as the limit as epsilon goes to 0, f of eta of I plus epsilon delta ij minus f of eta of I divided by epsilon. And here delta ij is just the usual Kronecker delta. So delta ij is equal to 1 if I is equal to j and 0 otherwise. Okay, so that's how I would write down a partial derivative. So now how do I get a functional derivative? So what we want to do to get a functional replace the I by the continuous label, like so. And so what we write then is that we can write this as the limit as epsilon goes to 0. So now my f depends on not eta of I, but eta of r. And then what do I have in here? Well, here I have delta ij, that's the discrete delta function. So what do you think is going to happen here? I'm going to get the continuous delta function, which is delta r minus r prime. Minus the function of eta, then divided by epsilon. And so this thing is the continuous limit of a partial derivative. And so we write this in the following way. As df eta of r divided by delta eta of r prime. So I want to just make sure you notice here the parallels. So let's look here. So here we have the variable j. You tell me what variable you want to differentiate with respect to, and that's the j comes in here in the delta ij. Okay, so you tell me what j is, and then I can tell you what is the derivative of f with respect to it. Now we've gone to a continuum, so now the label over here, this is the label j, that's now become the label r prime, and there we have the label j has gone to r prime, and then over here we tell you what we're differentiating with respect to, and that's the thing that comes in over here. So it's very important when you write down such a differentiation that you have these labels in it. Okay, so any questions about that definition before I give you some examples? Okay, so here's some examples. I want you to check them for yourself. So the first thing you might ask is what is, whoops daisy, wrong thing. Let's just get some practice with doing this. So what is d eta of r by d eta of r prime? So you might say, oh, well, I have no idea, but let's think about the definition. So this is just the continuum limit of d eta I by d eta j. And d eta I by d eta j, so think about I being x, y, or z. So d eta x by d eta y would be 0, d eta x by d eta x would be 1. So this would be delta ij in the discrete case. And so in the continuum case, this will be just the delta function, the Dirac delta, delta r minus r prime. Any questions about that? Okay, let's do another one. So next one I'm going to do is this, d eta of r, and then the integral d r prime eta of r prime. Okay, so again, remember that space is just a label. So one way I could do this is I could take this, this differentiation and bring it inside this integral, and then I'd have the integral, and this is integral over all of space, I'd have this integral of d of this operator, this derivative operator acting on this, which we already saw as a delta function. So the integral of a delta function is just 1. So you know that that's just going to equal 1. Okay, so you should check that. And then the last one, I definitely want you to check this one, is let's suppose I differentiate with respect to eta of r, and now I'm going to integrate d r prime 1/2 the gradient of eta of r prime squared. Okay, so of course all of these things I want to do because we're going to use them in statistical mechanics in just a minute, but let me tell you what the answer is for this one, and this would be perhaps not obvious to you. This is minus del squared eta of r. And I want you to notice that you tell me what r is. This thing here, the r prime, is just a dummy variable, so the answer doesn't depend on it. So this thing on the left-hand side is something that depends on r, the spatial label which you end up with. And so the right-hand side, which is the answer, does depend on r explicitly. Okay, so I want you to check these. And when I do this in class, in person, I will literally take 10 minutes and let you just sit there and do these calculations, but I don't want to do that right now. Okay, any questions? Yeah, go ahead. Yeah, any questions?
Yeah, thanks. In the last line that you wrote down, is there any assumption of what happens at the boundary, or is that true for arbitrary boundary conditions?
No, there is an assumption. So here I'm basically assuming periodic. There could be boundary terms as well. So the way you would do this is you could do this by integration by parts, for example. And
Yep.
so you can check that. So I want you to check that for yourselves.
Okay, got it. Thank you.
Okay, but in the usual case, we don't need to worry about that. Okay, so in the homework that I will send out, you will have a problem there to practice doing this, and the thing that you're going to see is that this this functional differentiation gives you the Euler-Lagrange equations in classical mechanics. So if you want to know how you go from quantum mechanics to classical mechanics, you probably know that you can write down a functional integral of the action of a quantum system, and then differentiate the action, which is the integral of the Lagrangian, and that will give you the Euler-Lagrange equations. And that same differentiation is the same differentiation that I've taught you here as functional differentiation. So functional differentiation literally is telling you the points in a functional integral that are stationary points, and from those you get the classical equations of motion. So if that sounds a bit strange to you, don't worry about it. The homework set, the homework sheet will walk you through how to do that, and you'll see that it's very similar to what you've already studied before. So what I'd like to do now is I want to move on and talk about the examples of continuous symmetries. So the first thing I want to give you as an example about is the Heisenberg model of a magnet. And all we do there is we start off with SI as plus or minus 1. That's in the Ising model. And in the Heisenberg model, we just say that SI is a vector. At that particular point in space. So the Hamiltonian for the system would be this, would be minus J, the sum I and J. And by the way, when I write down this symbol here, this means I and J are nearest neighbors on the lattice. And then the dot product of these vectors, and then the dot product of the external magnetic field with the magnetization. So that would be the Hamiltonian for a Heisenberg magnet in 3 dimensions. And notice that what's special about it is that this term here, this just depends on the angle between the spins. Right, because SI dot SJ is the magnitude which is 1 times cosine theta. So we're going to say that the magnitude of these spins is equal to 1, and so this just depends on the cosine of the angle between them, if in some direction. So I'm not going to dwell on that. So what it means is then, if I were to rotate all the spins in the system, will not change the angle between neighboring spins. And so what that will mean is that the Hamiltonian of the spins will be the same as the Hamiltonian of the rotation, or the rotation matrix acting on the spins. And so this R here means a rotation matrix. And I'm just going to talk for 2 more minutes and then we'll quit for today. So let me draw my lattice like this. And let's suppose I've got 2 spins here and here. I've got other ones, but I'm not going to draw them. And now I rotate them by the same amount. Okay, so here what I've done is I've done a rotation. Okay, so that's what the picture looks like. Now, what I want to emphasize to you is that this is a rotation in spin space, not in the lattice space. So I rotated the spins, but I kept the lattice fixed. So in other words, this is an example. This is an order parameter symmetry of the system, not a space-time symmetry. So it's an order parameter symmetry of the Hamiltonian. So we say that the Heisenberg Hamiltonian has rotational symmetry, but it has rotational symmetry in the order parameter space, not in the space in the lattice space or the physical space. Okay, so that's where I want to want to finish for now. So let me just summarize that. So when we talk about symmetry operations, we mean in order parameter space not real space. And so those are the symmetries that we're going to be interested in here. And then the last point is that the dimension of the order parameter space is not necessarily the same as the real space dimension. So I could have a vector Si, which is S1, S2, S3, S4 up to Sn at the lattice site I, and I could be in d-dimensional space, i.e. d equals 2 or 3, and n is the dimension of order parameter space. And they don't need to be the same thing. Okay, so with that, I'll finish today's lecture. And so let me stop the recording, and then I'll